I'm delighted to have worked closely with Jamie over the last few months to really understand the challenges Portsmouth Water face and where our solutions can be applied. Jamie and I will now summarize the progress we've made working together in developing genuine outcomes with the ultimate goal of achieving calm networks and extending asset life. Firstly, for those of you who don't already know us, I'll give a very short introduction of informatics. Go to the next slide. Thank you. So informatics was founded in 2015, and over the last 5 years, using the intellectual property we've developed in conjunction with Imperial College, we've worked with a growing number of customers, particularly in the UK, worked with many of the people who are attending the conference today, but also worldwide to understand the problems we can really help solve. Our solutions have been widely developed, leading to significant business growth over the last few years. Now, our latest product offering is called Arboristi, which, again, in close collaboration with Portsmouth Water, has allowed us to demonstrate really tangible benefits. So I'll talk a little bit about Arboristi. So what is it? It's, in summary, a digital tool can only be as good as the accuracy of the input data, particularly when developing real-time models. It has to be good input data. Arboristi is truly sensor agnostic, but it does benefit from the highly accurate high-frequency pressure data we can provide from the informatic sensors, amongst other inputs, including flow. And what we can create is a calibrated live hydraulics-based model. From this model, we generate outcomes which can be used directly in decision-making, particularly at an operational level, operational and strategic, in fact, which Jamie will talk a little bit more about later. And you'll see some very clear examples in the next few slides from Jamie. Our goal, of course, is to achieve calm networks and extend asset life. And when we talk about asset life, we're not actually just talking about pipes, although those are critical, but also all assets on water networks are impacted by non-calm networks, by transients, by those kind of effects. So I'll now hand over to Jamie to talk about the Portsmouth Water Network in more detail and the journey they're taking towards a digital twin.
Well, thank you, Robin. And Pauline, can you hear me? Excellent. That's a good start.
Yes, I can.
Networks are complicated, and understanding what is really happening within them is very, very difficult. We have different pipe materials that leak and fail in different ways. We have parts that are pressure managed and other parts are boosted. Our customer demand can be erratic and change from day to day or from season to season. And new sites are added to the network often. Our networks basically are regularly changing beasts, and no 2 days are the same. So why do we only update our network models once every 5 years? The answer used to be that we could not afford the sensors. But now we have more sensors, flow, pressure, noise data than ever before. The answer also used to be that there's not enough signal on our network. In the world of IoT, that has massively improved our data communications. The answer also used to be that it was not needed in order to achieve our targets. With the 50% leakage by 2050 and the reducing interruption to supply challenges out there, it means that is also no longer the case. Now we need to have faster and more informed responses to incidents than ever before. We need to get much better at targeting our main renewals and to prioritise our maintenance. We also need to save as much money as possible, and also, perhaps most importantly, stop causing a lot of our own issues on the network. Now is the time for us to take all of our data and put it to its best use, to create real-time calibrated and automatically updated network models, and to actually start understanding what is happening on our network. So at Portsmouth Water, we've been working with informatics to explore what benefits a digital twin could actually bring. My first example is a PRV failure that was on our network. In this instance, Arboristi was able to determine a potential issue, and and allowed us to send out a PRV technician before the PRV would fail. This early warning gave the technician time to resolve. It also gave our operations teams time to prepare for the worst. In an ideal world, the PRV would have been resolved and there'd be no burst on the network and everyone can be stand down. The crisis averted thanks to the early warning. Unfortunately, in this scenario, the PRV did still fail before the technician can actually fix it. And it caused 3 bursts on our network. But our teams were ready and sprung into action immediately. The 3 bursts were found and fixed quickly with no interruptions to customers. The crisis was managed thanks to the early warning system. My second example was a digital twin. Benefits can come through network calming. In this example, a customer reports severe pressure fluctuations on the network, and we deploy informatics sensors who, through the clever Cpis score, which is an algorithm that's kind of works out what stress is happening on the network. They managed to determine that our network in this area was under considerable stress. So ideally in a network, a Cpis score should be no more than 500, and we had 90,000. We had transients every 6 minutes. We had major pressure changes on the network throughout the whole day. And something was obviously very, very wrong, even though it was below a PRV, a monitored area. So we worked together with informatics in order to identify a potential solution, and this did prove to calm the network. Unfortunately, this solution needed additional network infrastructure, and so therefore we had to plan that in, but we did, and it was installed, and it did lead to the network being calmed and a significant reduction in those pressure fluctuations that the customer was experiencing. Things were still not perfect at that point, and so we have continued since then to further identify issues on the network and continue to calm the network as much as possible. Through work that we have done and also other water companies have done, we estimate the network calming, that if done over the whole of the Portsmouth water network, will reduce our burst rate by 18%, and that is not to be sniffed at. Our third example here is a large user in that requested to take a large amount of water in one go over a week. We modeled this and set out a kind of flow profile based on our out-of-date model. The user started using, and informatics came in at this point and pointed out that the water being taken was having an effect on the network and was causing additional stress. They proposed a solution to fix that, which did drop down that Cpis score, and then after the water was stopped being taken after a week, the network was calmer than it ever had been before. Unfortunately, in this instance, there was a burst a few days later, and what that does is it's really told us that we can't base any of our analysis based on out-of-date network models, and it's really very important to have the latest data. As said before in other presentations, it's very much a case of rubbish in, rubbish out, and very much a case of having great in and great out. A final example here was a lot that happened on the network this summer. There was a massive increase in demand through COVID, and it happened in certain areas, and this was one of them, and we started to get some very low pressures on certain parts of our network. We went out and investigated and just made things worse, to be honest, and therefore over to informatics in order to try and investigate what was wrong. Our technicians have said that all valves were open, and we believed them. But Robin and his team did not, and they argued that there must have been a closed valve on a network. we double checked this valve, and it turns out informatics were right. And so, taking Jez's palm analogy to the next level, hopefully, you can see that and the life of a leak. It's also taken from work from RPS as well, so I can't lay claim to any of this. But you can see there's the prevent, awareness, location, amend time. And for us, I've identified 4 areas now that I'm really keen to make big improvements in order to improve the our leakage figure and reduce leakage as much as possible. And arboricity is certainly going to help us with calm networks and prolonging the time before a leak occurs. And also you can see how it also will work in the future for automatic identification of leaks and location of leaks, similar to what Tom and Daniel proposed in the last presentation. And so to the actual tangible benefits. I've mentioned the 18% reduction on bursts, but we've also estimated a 12% reduction on repair costs and a 23% reduction on detection costs. That means we are able to stay at our current level of leakage detection and repair going forward, whilst reducing leakage. We've also started looking at other benefits such as operational and strategic benefits. We've seen a huge benefit to operations, of course, as we explained in here, but also into that long-term planning. And again, it very much comes back to the rubbish in, rubbish out. And through having far more accurate data being put into our models, into our planning to prepare for our business plan, we will see far better results out of it. I'll now pass back to Robin.
Okay, thank you very much, Jamie, and thanks for going through those case studies really that we've been working on and been really close to over the last few months. I think there's an interesting question from Joe, which I'm sure we'll come back to about Staunton Street. Now, I mean, just really as a quick summary, what we talk about this arboricity thing. I hope people have come across it. It's a new product for us. And really just to clarify what it is and why it makes such an impact. It's taking on board real-time data, flow, pressure, transient, and noise. So it's able to use all of those characteristics. It's yielding real-time network models. And some of the key points here are that it's calibrated and automatically updated. So as Jamie said, we're not relying on 5-year-old models that have been created that are almost out of date the next day. It's taking live data and using it in a much more sophisticated way than has been possible before. And what does that give you? It gives you full network insight, and we deliver this as a service offering, and we look forward to working with others in deploying these solutions across the challenges that each of you face. We've just shown some examples today. So really, thank you from Jamie and I for listening, and we're hoping there's going to be a bunch of questions because it's an interesting subject, and we're passionate about talking about it. So thank you very much.
Thank you, Robin and Jamie. And it is a fascinating subject. And the first question from Joe Parker. What was the cause of the fluctuation?
I could probably spend a whole presentation on just this alone. But in the interest of time, I'll very quickly say that there's a mixture of pumps at the large blocks of flats, a number of shut valves after main renewals that have been done and put back correctly, a number of valves that have been shut for a long time that were unknown to be shut. In Portsmouth, we have lots of valves, and that means that they're open when a right-hand valve is normally shut, and so it causes a lot of confusion on the network. There is also, as well as that, a separate large user in the area as well that was causing a lot of confusion, and we believe to be the main reason for the transients, but was actually completely fine and was not causing any issues at all. So it's a very complicated network right in the middle of a city, and our network's very widespread. It's not like a DMAs that are very close, and so therefore in this area there was tons and tons of things it could have been very close to each other, and lots of blocks of flats. Not quite London level, but lots of blocks of flats, and trying to determine which one it was very, very difficult without Robin's help.
Great, thank you. And we have a question from Gertch Chana. What physical changes did you make to the network to reduce
to open up the network and to rezone it in order to take the part of the network that was where the transients were and put it onto a larger pipe network. And so it was fed in from a different direction in order to minimize the amount of the effect the transit was having on the rest of the network. So as we kind of zoned in these block of flats and moved them away from where the pressure fluctuations were happening elsewhere, the customers complaining, and took it straight to the trunk network, really. And so in that case, that's what we did. In other areas, there are separate things that we've done, such as, and obviously always talking to the maintenance people of these flats to try and improve and reduce these transients across the network through more capital intensive solutions.
Okay, we've got a couple more. Distribution across the whole of the UK. Is that one for Robin?
Sorry,
maybe?
I just froze there, but
froze for me too.
Yeah. And Robin, do you want to go just for
yeah, sure, absolutely. I think we all suffer from I don't know digital twin confusion in some respects, because what is a digital twin? I mean, the simple realization that we talked about with Portsmouth Water is really having a mirror of the network, so even a technician actually at an asset doing a job can actually understand how the systems work. Now the question is obviously how close are we to having that? With the wealth of data we've got, and focusing on outcomes rather than data lakes that I feel we can drown in, it's using the right information. So having pressure data, having pressure head, having flow data, having noise data alongside this, bringing those elements together. And what we've done with Arborist, but also working with the modeling packages, so working with Innovyze, for example, to understand what models exist already and to augment those to make them live, is now a reality. And it's only recently, because of understanding the algorithms that are required. I mean, there's some basics in there, but you need to put them together in the right way, combine all those attributes together properly. And what we've been able to demonstrate is that you really can understand the network, and even the simple cases where the Portsmouth Water team were convinced that the valve had been opened. We ran the models, that just can't be true. So by a simple process, we could deduce what was going on and then resolve a problem that had been kicking around for ages. So it is possible now to do this, and this is what we are doing with Portsmouth.
Great, thank you. And a question from Chris Rees. A very interesting presentation, both. Great to see a mix of sensor types used. What is the average number of sensors you need per DMA to allow the model to run effectively?
So it's interesting with the Portsmouth area, because there are large zones tend to be different to many of the other UK utilities, where DMAs are a particular size, sort of varied, but much bigger in Portsmouth. Now we've always said across a typical DMA that around 4 or 5 devices are required. What we do with Arborist, and this is part of the service model, we start off with a higher density, and then we back away if we need to. So we support and service the application. So we're not asking customers to buy the devices. So it becomes a slightly different proposition, that it isn't buying an asset, deploying it, letting it get out into disrepair, we can go in, deploy the devices as appropriate, and it could be the inlets, key assets, outlets from the system PRVs, pumps, and so on and so forth. So we can design a deployment scheme, understand the network, and then back away. If it's particularly calm, we can back away. So, but typically 4 or 5 devices per DMA is a good number, and applying that can be an expensive proposition across many zones, and perhaps focusing down on the critical areas initially to prove the value of the analysis and the model, but of that order. Hopefully that answers the question.
Okay, thank you, Robin. One question from an earlier discussion I have here. What makes your Cpis score unique? And how is it different from just measuring the magnitude of the transient?
What we do with Cpis, we developed an algorithm that understands the pressure fluctuations. Well, we have the benefit of 128 samples per second, so we can see those variations, and what we do, we actually compute it on the device. So the device itself is listening out for the variations in pressure, and it's accumulating those into this metric. What it can then do is it can alert anomalous behavior in the trend. Now, what it was able to do in Staunton Street, for example, was to identify really quite a horrific level of pressure volatility, dynamic pressure changes in the network, which were ultimately very damaging. And the scale they were at was literally almost literally off the scale. And using that metric, we were able to understand the improvements that were made with the rezoning and the work that Jamie talked about. And actually the journey continues, because if you look at Staunton Street, ignore the first part of the scale, it's still quite high. So the impact of pumping schemes locally in the flats, but also potentially other aspects of the network, this metric allows, by really understanding how pressure is working, not just the magnitude, but the variability. That's what gives its unique benefit, and that's what gives unique insight and the ability to deal with those issues and turn them into outcomes.
That's great. I think that's all the questions we have for you for now. So thank you very much. But again, people can speak to you later in the sessions outside. So thank you both, Jenny and Robin.